Okay, good evening, no, good morning. So, um, just next lesson on Wednesday is cancelled, so no lesson Wednesday. Okay, so the program is as usual, lesson only on Monday. Okay, next Monday. So not next lesson is 20 of November. Okay, no Wednesday 15 but Wednesday. Okay. And so the program is as usual. We have a lesson on Monday, not Wednesday, and we have time to finish our lesson before the middle of December. And okay, so last time we have seen many things, and the last things was the floating point representation. Okay, maybe you remember something, and you have seen something about the floating point representation. You have seen this exercise that we have done together last time. So in this exercise, you can see how it's possible to represent floating point numbers, or rather numbers with the decimal points, okay, in which we put the decimal point in a floating position, not in a fixed position, like in the fixed point representation, but we put the decimal point in the floating point representation, okay? So for example, here you can see how it's possible to represent that decimal number, 4,500 and so on. The first step is to convert the decimal position representation in the binary position representation. Okay, this is the first step. The second step is to convert the decimal part, but I will give you the conversion, so you have to you can skip this step. Okay, since I will provide you a table with the decimal list value, so the binary positional representation of the decimal part. Okay. Then we have to apply the normalization procedure on what? On the whole number you create. You can create this number merging the integer part and the decimal part using the decimal point, of course. Okay. So you have to merge this part and the following one. And then in this case, for example, if you have the decimal point here, you have to move this decimal point after the first position. Okay, so here, after the one. And then you have to use an exponent to translate, to convert this number in the following one. Okay, so in this case, we are moving the decimal point in 12 different positions. Okay, if you count 1, 2, 3, 4, 5, 12. And so we use as exponent the number 12. Okay, it's very similar to the scientific notation that you use in the decimal position representation. Okay, and then the last step is to compute the exponent. Okay, the exponent is always positive, so remember to apply the biased representation. In this case, the standard introduced by IEEE. If you remember, this is a standard introduced by IEEE, the Association of Engineering, to standardize this procedure. This standard doesn't use the choose complements, but the bias notation. So in the bias notation, remember that we translate all the negative numbers in positive numbers. Okay, there is a shift, and we use a shift using the value of the shift is a number, in this case 127, that we obtain with the equation that I show you, 2 to k minus 1. Okay, in this case, so we have 12, we add 127. Okay, the result is this one, and then you have to convert this decimal number in the binary representation. Okay, in the binary number. So in this exercise, you have to convert two decimal numbers. Okay, so you have to apply the conversion between decimal base to binary base 2 times. The first is in the first step, and the second is when you compute the exponent. Okay, that's all. When you have computed the exponent, then you can create the final representation. Remember that in the first position, there is the sign. So we have 0 for positive, 1 for negative. Okay, this is the standard. So in this case, we have a positive number, initial positive number. So here we have the 0. Okay. In the second case, the other exercise that you can find, we start from a negative number. So here we have 1. That's all for the sign. Then we have the exponent. The exponent is the binary number that you find here in the final step, and then you have to copy 1 0 0 0 1 0 1 1 in the position of the exponent. And finally, you have to put the significant. Okay, the significant is this number, normalized number, is the mantissa, okay, number. And remember, it's very important to remove the first one. Okay, so the first one is removed in this case. And as you can see here, we have this representation. You have to just copy the bits of this representation. Okay. Remember that in the single precision format, the final number is a 32-bit final number. So if you have some free spaces, you have to add 0 until you achieve 32 bits in total. Okay, so you count 1, 2, 3, 4, 5, and then okay, have to write 7 more zeros to have a 32 bits number. The second exercise is very similar, since we have negative number. Okay, as you can see here, we have a lower amount, so it's more easy. It's easier to convert from decimal to binary. So you start from 113, then you have the binary representation. The second step, you can skip, only take the value from the table. Then you can merge the first number, the second one. You have to move 3, 4, 5, 6. You have to move the decimal point for 6 position. And then this number becomes 1.110000111 times 226, since we have moved the decimal point for 6 different positions. Okay. The exponent is 6. Then we have to apply the Basta representation. The value that we have to add is always the same. Okay, so 127. So you obtain this number, then you have to convert this decimal number in the binary number. And then we create the final representation. Okay, so 1 negative, exponent, and significant, that is the mantissa, remember, without the first one. And as you can see here, we have this representation, and then I have to fill the 32 number with all the other zeros that I can put in the last part of the number. Okay. This is one of the exercises that you can find in the final exam. Okay. And in the last part of the course, I will upload some slides with all the exercises that you can find in the final exam. Okay, if I remember well, there are 4 or 5 categories of exercise, and this is one of the categories. Okay, then you have the addition with sign numbers. Okay, using the choose complements representation, and many other 2 or 3 other categories of exercises. Okay. Questions about? No. Okay. And also about all the other, the last lesson. Everything was clear. Hope so. Okay. So today is time to see other digital representations, since we have seen how it's possible to represent numbers, values inside the computer using the binary positional representation. Okay, how it's possible to write or store a number in a computer, a signed number, an unsigned number, a number with the decimal points in a fixed position, number with a decimal point in a floating position, and so on. Okay, so we have seen how it's possible to represent numbers, values, okay, different values inside our computers. Today, we are going to how it's possible to see how it's possible to represent, for example, characters inside a computer. Okay, is another type of data that we can have inside the computer. So how is possible to represent characters inside a computer using the binary code, the machine language, that is the binary code, or also how is possible to represent images? When you take a photo with your smartphone, how is possible to save this image inside your smartphone, since your smartphone is a computer? So you have to use the machine language to handle the image and save the image inside your computer. So you have to use the binary representation to represent images. How is possible to do that? And finally, also sounds. How is possible to record an audio and store the audio, use the audio inside the computer? We're going to see how it's possible. So we start from characters, okay? Each computer has a set of different characters, okay, that can use. Also in your computer, you have a specific set of characters that you can use. The important element to know is that each character is assigned to a number. So the solution to represent characters in a computer is using numbers, okay? And the mapping of characters and numbers is called character code, okay? So we have a map that store all the conversion between numbers and characters, okay? And characters and numbers. Of course, it's essential that if you want to communicate between two different computers, we have to use the same code, the same characters code, okay? It's important. And for this reason, since we want that all the computers all around the world have the ability to communicate, okay, we have introduced many standards that are convention that we want to use, we have to use to make possible that two different computers are able to communicate together, okay? If you don't use the same character code, for example, in many mails, you can see very weird symbols, okay? Instead of letters, you can see weird symbols. In this case, there you are using not the same character code. Okay, one of the first standard or convention introduced in computers, in the computers field, is the American ASCII, or in Italian also ASCII, that is stands for the American Standard Code for Information Interchange, okay? Information interchange. You remember, this is a standard that we want to use in order to create the possibility to communicate between different computers for information interchange. Okay, introduced in 1968, so pretty old. In this case, remember, each character is assigned to a number. So in this case, each ASCII character is represented with 7 bits. And you know how many characters we can represent here, since we know that if we are using the binary representation and we have 7 positions that we can use, the maximum value the maximum amount of different representation that we can have is 2 to 7. So in the ASCII convention, we can represent 128 different characters, okay? And for example, there are other rules inside the ASCII convention, for example, that all uppercase letters come before lowercase letters, or digits and many punctuation marks come before letters, okay? So as you can see here, we don't have only characters, or we have characters that consist in letters, punctuation marks, digits, and other symbols that we can use when we type a text, for example. Do you think that 128 is a good value to represent all the letters, all the characters, or not? Is more, yeah. So ASCII code is the first one of the first important convention, but unfortunately we have a very few amount of bits, so it's hard to use this convention to represent all the characters. And we are going to see how it's possible to solve this problem. Before that, we can see the ASCII table. This is the table we have seen here, the character codes, okay, that contain the mapping between the numbers and the character that we want to use, okay. For example, the letter T uppercase is the number 84, okay. Here you can see in yellow the decimal representation, while here in white you can see here the binary representation. Okay, so the letter T is the number 84, and this is the binary representation. As you can see here, we have all the Latin letters, uppercase, lowercase, but we have also, for example, other punctuation mark, but we have also we have the backspace, we have, for example, the space. Somewhere there is also the space, since if you think the space between letters within words is a characters. So we need a representation also for the space, okay? And we have the brackets, and we have many other elements. You can use the ASCII convention using these keyboards, okay? And if you type the numbers that you can see here using the numpad, okay, so you with the laptop is not easy. I don't know the procedure to obtain the characters contained in the ASCII code, but if you use this keyboard, you can obtain one of the following characters, the listed characters, okay. So you can try at home using, for example, a Blocknote app, and then you can try to, you have to hold the Alt button, and then you have to type the number of the characters that you want to represent, okay. And then you can obtain, for example, the number 7, the letter U, and so on. Unicode, okay. The problem with the ASCII is that we use only few bits to represent the characters. Only 7 is not enough, since, as you can see here, the ASCII has been proposed in the USA, since the computer industry grew up mostly in the USA, especially during the 60s and the 70s, okay? That's why we adopt the ASCII character set. The problem is that ASCII is okay for English, okay? For example, for English, American English, British English, and so on. But for example, we have many problems with French. For example, these are only 3 examples, but you can have more and other problem. For example, we have problem with French, Italian languages. In these languages, we have accents, also in other languages. Okay, remember, this is only an example. But in French and Italian, for example, we need accent. And as you can see here, we don't have accent here. So this is a problem. In German, we have the diacritical marks. I don't know what is a diacritical. I think the 2 points over a letter. And also in this case, we don't have diacritical marks here in the ASCII convention. And the other very important problem is that some languages need an entirely different alphabet. You can think, for example, Russian language, Arabic language, Chinese, Japanese. We have other symbols that we have to use, okay? And these symbols are not here. So the ASCII convention is okay only for English. For many other languages, we have several problems. One of the first solution proposed was extending the ASCII, okay, using the so-called Latin 1, and was an 8-bit code representation. So they had a single bit of representation. So ASCII 7 bits, Latin 1 8 bits. So we can have more representation. We can have more values. We can have more characters, but that was not enough. That's why we introduce they introduced a consortium that create a new system, a consortium made by different companies that were in the computer world, in the computer field, and they create a new system, a new convention, a new standard called Unicode. Okay, that is one of the most important current standard that we are using with computers. In this case, we have a 16-bit code, so not 8, not 7, 16-bit code, and some different extension of the Unicodes are up to 21 different bits. Okay, and but in the base version we have 16-bit symbols, and then we have this amount of different representation, or rather different characters that we can have in this convention, in this standard. Okay, so around 65,000 of different code points. Code points stand for the single characters that we have in the Unicode. Okay. Also in this case, this is a good solution. 16-bit up to 21 bits. Okay, we have many different representations, many different code points, but also in this case is not enough, unfortunately, since, for example, words, languages collectively use about, I found this amount. I'm not sure that, but you can understand the complexity of this problem, since all around the world we have 200,000 different symbols. So 16 bytes are not enough to represent all the symbols that we need in the world. So probably we are going to create another evolution of the Unicode standardization, since we need more and more characters to represent all the languages around the world. Okay. And also, as you can see here, okay, Latin, what is one of the most used languages, representation language in the world, that so is okay for English, and that's why Latin is used in English-based countries. But for example, as you can see here, there are many other countries that need specific alphabet, specific accent, specific characters that we have to take in account in our representation. Okay, and we have finished characters. So, do you have questions about characters? Remember, one chart of characters is a number, okay? And the mapping, we need to know the mapping between characters and numbers, okay, to define our convention. Okay, images. Next year, we are going to use a lot of images, since in the second year, you have the machine learning exam with me. And in our exam, we are going to train intelligent systems that are able to create knowledge starting from images. And that's why images, I introduced here images, and images in particular, in general, are pretty important for the computer field. Okay. So how is possible to represent images? You can see here the solution. An image for a computer is a matrix of values. Okay, here you can see an image, an example image. In this case, the letter A. Okay, and here you can see the visualization of this image for a computer. A matrix of different elements. In each element, okay, or rather, in each element, the name of the element is the cell. In each cell, we have a value. Okay, this cell is named pixel, since the name pixel stands for picture element. Okay, so each cell is a picture element, or in other terms, is a pixel, a single pixel that we use to represent the image in a computer. Okay. With gray level images, but also with color images, in each pixel, we have the value of the brightness, okay, the level of the light that our sensor is able to acquire from the world, from the scene that we are going to acquire with our camera, with our sensor, Okay. So, for example, in this case, we have where we have the white color or the white brightness, we can say we have the value 1.01. That is the maximum level of brightness in an image, the white color, of course. Conversely, where we have black, here we have the value 0. The black color is the minimum amount of brightness that we can have in the image, of course. So we have the two extreme components, black and white. All the other level of brightness correspond to other level of brightness, of values, other range of values. So for example, here we have a gray, and this element is 0.6. Here is 0.5, and so on. Here, what we have, 0.9, and so on, okay? So we have different level shades of gray, and then we can map this level in our numbers. So even with images, we use numbers to represent our data, okay? We use numbers to represent numbers. We use numbers to represent characters. We use numbers to represent images. And for the sound, what we use? Numbers, okay? This is the solution of the problem of today. Okay, usually we don't use 0 and 1 in computers, but we use 1 byte of information. So in each pixel, we have 1 byte of information. We have 8 bits of information. So how many values we have in 1 bit? The maximum value is, we can have 256 different values, and the maximum value is, you know that you have to apply the formula q to key minus 1, where key is the number of positions that we can use, in this case 8 bits. So the maximum value that we can have is 2 to 8 minus 1, 255. So normally, traditionally in images, in computers, in each pixel we have values that start from 0 and goes to 255. What is the spatial resolution of an image? Okay, is the number of lines that are contained in this matrix. Okay, so in particular is the number of columns, or also the width of an image, times the number of lines or rows of the matrix. If you do this multiplication, you can obtain the spatial resolution of the image. In our case, for example, we have 12, I don't remember, I think is the width times 14. So the spatial resolution of this image is 168. Okay. If you take a photo with your smartphone, you can see the details about the photo, and you can see the spatial resolution of the photo. And I think that here you have thousands of different values, not only this small value, since the resolution of your sensors is pretty high. Okay, so you have many, a very big spatial resolution. Okay, here we discuss the representation of gray level images. Okay, but how is possible to represent images with colors? The base idea is the same, to use a matrix of different elements. But in this case, we have not only one matrix, but we have 3 different matrices, okay, of colors. And each matrix represents a color component. Usually, we refer to these matrices as channels, okay? So in this case, 5 times 10 color image has 3 different channels, okay, of equal size. In each channel, we have a matrix in which, for example, with a spatial resolution equal to the original image, so 5 times 10. The first matrix is the red component, okay? The second is the green component, and the third one is the blue component. The red, green, blue component is the RGB format that we can use to represent our images. And several studies have shown that it's possible to have all the possible, not possible, but many colors using different combination of red, green, and blue. Okay, so how is possible to represent images, color images in computer? We use a matrix of elements called pixels. And in particular, we have 3 different matrices, and each matrix represents a color component. If we are using the RGB format, these components are red, green, and blue. We can use also other convention, other standard, of course. Okay, so we have many standards in our computer field. So we don't have only the RGB convention, you can say, but we have many other color spaces. These conventions are called color spaces available. For example, we have the HSV, HSL, and many others convention. Okay, you can find on Wikipedia all the possible convention that we can use with images. But one of the most used convention or color space is the RGB one. Okay, I think that maybe you have heard something about the RGB. Okay, since it's one of the most used convention. Okay, with the other convention, with the other color spaces, we have 3 components. Okay, but in that case, we don't use the first component for the red, green, and blue, but we use the components for other values. For example, we have with the HSL, we have the first component is for the hue. The second is for the saturation. The third is for the lightness, that is very similar to the brightness. Okay, or here you can see a graphical representation of that. Since the saturation is the I don't know how to express in English, is how the color is strong. Okay, you can say. Then we have the lightness. Okay, from black to white, and then we have the real color, the hue. Okay, turning around this representation. Okay, so the takeaway is that there is not only the RGB representation in which we have red, green, blue, but it's possible to have also other representation, which for color images. But the RGB space color is one of the most used convention in the computer field. Okay, so this slide is about the topic of how it's possible to save images inside a computer. So an image can be stored in an uncompressed way, so we don't compress the information of the image, but also we can use a compressed format. So we compress the information, we shrink the dimension of the image in 2 different ways, in a lossless way or in a lossy way. Okay, in lossless compression, we don't lose information, while with the lossy compression, we lose information. First example, JPEG images. You know, I think JPEG images, okay? JPEG images, JPEG is a lossy format. When you save images with the JPEG name, with the JPEG extension, or in the JPEG format, you are losing information, okay? So that's good for your memory, since you can store more images in your memory, since you save space, thanks to the lossy compression, but also you lose quality. If you want to don't lose any information, you can use, for example, the GIF format is a lossless compressed format, or also the PNG format. Okay, PNG is similar to the GIF, is the evolution of GIF, PNG, okay, is a lossless format. Lossless, so in this case, we have compression, okay, but we don't lose information. That's why usually with PNG, we have higher quality output, higher quality images saved in our disk. Okay. What's the difference between JPEG and PNG? Is the space required by the image to be so. Okay. So in JPEG, for example, we have an image that is about 400 kilobytes of information, while with the PNG format, we have 4 megabytes of information. Okay, there is a huge difference between these two formats. You can see here an example. PNG, JPEG. Okay, this is a synthetic image since we have an image that is created by a computer. And as you can see here, there is a zoom that shows you the difference between PNG, no information loss, and JPEG, information loss. Okay, here the projector, I don't think is help us to see the differences, but you can see on the slide, okay? So for synthetic images, it's better to use the PNG format, for example, okay? While with real-world images, it's better to use the JPEG format to save space. As you can see here, in the comparison, you cannot see any differences between the comparison of these two images. Okay, they seem the same image, but in the first case, we are using the PNG format, and the weight, the dimension of this image is around 4 megabytes, 10 to 6, okay, bytes. While with the JPEG, we have the very similar visual quality, but the space is only 500, around 500 kilobytes of information. Okay. That's why if you buy a new camera, Canon, Nikon camera, usually one of the default formats, okay, set in your camera is the JPEG format, since you can save a lot of different images, different photos in your SD cards, and the quality is pretty good. Okay. And here you can see also you can see in a visual way, in another visual way, the differences between PNG. The first half of the image is in PNG format, while the second half is in JPEG format. And as you can see here, I don't know if you are able to see that, but the quality is very different. Okay, we have finished images. So today is I think, light lesson. Okay, not the previous one, but not like the previous one, but okay. And okay, so we have seen characters, images, and finally sounds. Here, to understand the representation of sounds, you have to recall the slide about analog versus digital signals. Okay, at the beginning of the second block of the slide, if I remember, or the first, I don't remember, but there is a slide that focuses about the differences between signal and digital, digital and analog signals. Okay, in this case, what we have, the sound captured through a microphone is captured in an analog way. So we need to pass from the analog world to the digital worlds. Okay, how's possible to do that? The first step is to quantize the first signal. So a sound wave, in this case, the red wave, is sampled at each time sample point. Okay, we define many points and then we sample the value of this curve, of this red line. Then we convert this amount that we found in the sample point to the nearest numeric equivalent. Okay, for example, here we sample this point. Okay, since we want to sample this point, and here we have the value 8, and then we pass the value 8 here, in which we have the same amount, okay, the same value 8. And then we can repeat this procedure to obtain, for example, in this case, this digital signal or the following one. The difference between these two digital signals is the sample rate, okay? That is the number of different samples recorded in a given period, okay? If we change the number of sampling points, we can obtain a more accurate or a lower accurate digital signal with respect to the original analog signal. Okay. Remember that, in other words, the higher is the sample rate, the closer is the recorded signal to the original. Okay. And you can see this difference in audio files. For example, if you use an MP3 format, usually what you have a lossy data compression, so you lose information with MP3. Okay? So MP3 is created to save space in our digital player. Okay, so we have a lossy data compression, but these allow a large reduction in file size. Okay, so that's why we use MP3, the MP3 format in our digital storage. But if you want an audio with a very high quality, okay, you have recorded a very beautiful song, you want to have the maximum quality possible quality. For example, you can use the FLAC format. That is, also in this case, we have a compression procedure applied to our audio files, but in a lossless way. So in this case, we don't lose information. So we maintain the quality of the audio in an excellent way. For just a parallelism, MP3 is similar to JPEG. Okay, we save space, but we lose quality. With the FLAC format is similar to PNG. We save the quality. We want to maintain high level quality, but we lose. We have bigger files, so we lose the opportunity to save more songs in our disks, in our storage. Okay, this is also the last slide for today's first part. Okay. Questions? No. Okay, so if there are no questions, we have many. Maybe we can have 5 minutes break, and then we can have the second part. We have 11 new slides about Boolean algebra. That is the new topic of the second block, so 2.2. Boolean algebra is quite a strong topic, so it's better to have 5 minutes break, and then we can move forward. Okay.
我现场有那种样子的。对，但这个赛呢不是垃圾吧？是涉及到全部。基本上不是，就是一种什么方式就并不干不出来东西。谢谢你这样自己打呀，封禁的，比较正常，你没有这个，就是对我来说，就是计算机，我是最为想说的，要先用这个设计思想。财政是怎么办？说实话，不要去学，我其实现在专门上去学这个，但是我就是被说我是被听的，但这其实不是，而是我的肉来说，你是我想吃的专业都。当然，是上这个而且是这个是吧？其实我们是非常喜欢的是，这个一个我看进去，然后就看下来。啊，那真的也啊，你们是说是多可怕？他可以每天都上这样3个小时，这个但是对我，我也是比较。所以这个这是正经的奶吗？我那个奶茶，我这个好多了。下次到我给你说，我在那个珍珠来，bubble tea， Max friend tea， now he gave me maybe just you and me and he made some bubbles. With the button. Yeah, so yeah, yes, we bring it from her house to the campus. Barbie. Like I bought.
Oh, you're a happy girl.
Actually, because the Barbie is beautiful. Because the Barbie is beautiful. So, I think actually. I They're laughing at me. I tried doing on that one time. Complain with you. Never tried other people. I have tried to but I never tried to do it. You must have.
Guys, you mean it's not wrong. It's here.
Are you always with memo?
Yeah, you just
Oh, you need to try you.
read this bubble inside the kind like here. But it's me plus him.
Okay.
Okay. It's me to it's me plus.
No.
It's just me.
Yeah, it's just you. They really the milk into the they put it to back.
Yeah.
Then you know words of you false to it and the
Super.
yeah, it's trying makes them to be like yeah. You can and
The bubble. I mean,
yeah, you can just make it by something flower.
but are made of kind of bubble with
They're even mounted down. I'm more. No, It's huge. No. There's no. You can never find them. Yeah, that's usually like you. What the bubble is.
Okay. So, Boolean algebra. Okay. 2.2 is the second topic of the second block of slides. Okay. So in part one, we have seen digital circuits, in particular specific digital circuits such as the central processing unit, the CPU. Then we have seen the memory, the RAM memory, the storage that we can use to store information. And also we have seen that it's possible to use the machine language to communicate with computers, okay? And unfortunately, the machine language is a sequence of 0 and 1. And so it's hard that a human use the machine language. And that's why we create the multi-level machine in which in each level we have a different and also a higher level language to use to communicate with our computers, okay? Machine language is connected to the binary code. The binary code is the possibility to represent information with 0 and 1 with the machine language, okay? And then inside the binary code, we have seen binary position representation, unsigned, signed, real numbers, representation of, we have seen today, characters, images, and sound, and so on, okay? So how is possible to merge the word about the digital circuits, CPU, RAM, but also machine language, and the binary representation? How is possible to use the digital circuits to create to compute operation using the binary code? Okay, and we are going to see how it's possible. So we have two main elements that we are going to see. The first element is gates. Okay, is an hardware element. Okay, is at a level 0 in our multi-level machine. With gates, we are level 0. Okay, gates are composed by transistors, so we are going to play with transistor. Okay, and the second element is a more conceptual element, is the Boolean algebra, is the algebra that we have to use to create intelligent systems. We can say to create arithmetical logical system using only 0 and 1. Okay. For example, you can use Boolean algebra to develop a specific digital circuit, okay, with a specific behavior, with a specific input. I would like to have a specific output, and I use the Boolean algebra to model the circuits, okay, to develop, to project all the components inside the circuit. Okay, so we are going to merge these two words, okay, binary representation and digital circuits. So we are going to introduce logic gates, okay. Remember that here in this case we have at the level 0 of our multi-level machines, okay. In few slides, I'm going to show you the transistor symbol. So we are going to play with transistors, okay? We are a very low level. Here you can see the recap of the previous slides. So we have the machine language, a sequence of 0 and 1. We want to use digital signal and then the binary representation, then digital circuits to use computers with the binary representation and also the binary information. So we are going to investigate the use of how it's possible to create binary digital circuits that are located at the level 0. Okay. The positive fact is, fortunately for you and also for me, it's possible to create these binary digital circuits using only a very limited amount of base elements, okay? Only 3 base elements, and these 3 base elements are called gates, okay? We can combine different gates that are the base elements to create different digital circuits, okay? And our computer are based only on 3 different gates, 3 different tiny electronic devices, okay, called gates. And remember, when we say binary digital circuits in particular binary, since we are using computers, and remember that binary means we have only 1 and 0, and at this level 0 is the fact that we don't have current, okay, we don't have voltage, or the amount of the voltage is very low, from 0 to 1. So here in this level, in this hardware level, 0 is the absence of current, absence of electricity, while the value 1 is the presence of current, okay, the presence of voltage. Typically we have from 2 to 5 volts. Maybe you remember the volt from your high school. Maybe you have seen the volt in your physics course, but it's the presence of the current. Okay, for now, for us also, it's not so important to understand the meaning of this letter, but it's important to understand that with 1 we have electricity, 0 no electricity. Okay, again, digital circuits are built through transistor, and in particular, gates are built using transistor. That remember maybe the lesson about, you remember maybe the lesson about the switches. Transistor is the last evolution of the switches that we have seen together. Okay, we have relay, we have vacuum tubes, and the third evolution was transistor, okay, introduced by the Nobel Prizes and blah, 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 okay. Milestone, okay, the lesson called Milestone. In that lesson, you have the evolution of the switches, and in particular of transistors, okay. So here you can see the definition of gates. Gates are tiny electronic devices that can compute function in a binary way using only 2 values, 0 and 1, okay. And you can see, for example, if you have open electronic device, maybe you have seen this component, and you have to know that inside this component there are our gates. So it's possible to see gates, okay. Usually they are located inside this small plastic piece, okay. From a graphical point of view, it's possible to represent a gate using for example, this set of different transistors. Okay, so we have the gates. We have several transistors inside, usually 1, 2, or 3 different gates for the fundamental gate. Transistor, sorry, for the fundamental gates. We have an input. The input is binary digital signals, 0, 1 signals, okay? And the output is, again, binary digital signals, okay? What we apply here is a function, okay? So this function is the transformation that we apply on the input to obtain the output. Now we are going to see how it's possible to build the gates. And with the Boolean algebra, we are going to see how it's possible to define our function to obtain a specific output using a given input, okay? So this is the Boolean algebra, how it's possible to produce the output using a particular function applied to the input. And now, in the following slide, we are going to see how it's possible to build the gate, okay? So using which transistor and how it's possible to develop a gate starting from, again, transistor. As I mentioned you before, the positive element is that we have only 3 fundamental gates. And again, we can use these 3 elements to create all the other digital circuits, okay? So in our computer, there are only 3 fundamental gates. And the first one is the NOT gate. So in the first position, as you can see here, we have the name of the gate. In the second position, we have the symbol that we can use to represent this gate on our paper, for example. And more important, in the last position, you can see a table. This table represents the logical behavior of the gate, represent the output of the gate given a specific input. Remember that in the gate, we have an input and an output, okay? And here we have the description of the input in the first column. In this case, the input is represented with the letter A, and we have a single input for the NOT gate, and X is the output, okay? NOT gate means that if we have 0 in input, the output is 1. If we have 1, the output is 0. NOT is the inversion, okay? So a sort of inversion, 1, 0, 0, 1, okay? Second gate, you are using also the NOT condition in Python programming language. If you type NOT variable, you mean the inverse of the content of the variable, okay? And gate, as you can see in this case, and also in the following one, we have 2 different inputs. Here we represent this input with the letter A and B, and only 1 output, letter X, okay? And as you can see here, there is also the symbol that is different from the NOT, okay? Here we have the symbol of the AND. The table that represents the logical behavior follow the fact that we have 2 different inputs, okay? So in this case, A and B, but we have only 1 output, like in the previous case. 0, 0, the output is 0. 0, 1, the output is 0. 1, 0 is 0. 1, 1 is 1. It's not the arithmetical behavior, it's a logical behavior, okay? It's a behavior of logic. You can apply this table also in the real life, okay? If you have 2 conditions, you can define the output of these 2 conditions using the statement AND, okay? Last digital gate, last fundamental gate is the OR gate. 2 inputs, 1 output, and logical behavior. And tell me if you recall this table recalled you something, okay? 0, 0 is 0. 0, 1 is 1. 1, 0 is 1. 1, 1 is 1. is the addition of two different, with the exception of these lines, okay?
Zero with
The carry. Yeah. Okay, so the intuition is that we can use these gates to implement the addition inside our computer, okay? So you can see that we are merging these two words. We know how it's possible to handle binary numbers with the binary representation, okay? And we know how it's possible to sum these numbers, okay? Since we have seen how it's possible to do the addition, okay? The multiplication, the division in other cases. And here we have a digital circuit that we can use to implement this function inside our computer. Okay, yes. The ALU is composed by this gate. And we are going to see how it's possible to use this gate to create the ALU. The ALU is level 1, okay, microorganization of multi-level machine. In level 0, we have the fundamental gates. So the organization of different fundamental gates create the ALU, but create also the RAM memory, create the central processing unit, the data path, and so on, okay? And okay, of course, there is also the evolution, okay? So last evolution in computers development has introduced some changes in currently, or actually in modern computers are based on other two types of, are not based on AND and OR gates, but on an equivalent form. Is very similar with some differences, and we are going to see why, okay? So that's true, okay? We can say that all computers are based on not and or, but for several reasons, in real computers, we use different gates here. Instead of the AND gate, we use the NAND gates, and instead of the OR gate, we use the NOR gate. Okay, we are going to see why. We save space. Okay, spoiler. We save space. It's possible to reduce the number of transistors that we use to build this gate, and then it's preferable to use these two gates in order to save space in our motherboard. Since we use less transistor, and then we can save space. Okay. Okay, NOT is called also inverter, since there is an inversion of a bit, is not important. As you can see here on the left, you can see the symbol and the logical behavior, okay? On the right, you can see the transistor that we can use to implement this symbol, okay? This is the real implementation of the NOT gate on modern computers, okay? And for example, just to understand the very general behavior, we have here the output. Remember that logical gates, digital gates have an input and one or two inputs and an output. So here we have the output, here we have the input, and here we have, okay, the component that we have seen together in the slide about transistors, so the emitter, the base, the collector. You have to remember that the base is the external signal that we use to control the transistor, that is a switch, okay? It's like my finger that I use to power on or off the lights, okay? It's this external control that we use to control the behavior of the transistor. If we apply a very low voltage on the input, so we are controlling the transistor, we stop the functioning of the transistor. We block the current here, and so from the power source, all the power source is route in the output. Okay, so in input, remember we have a very low voltage, so 0, and in output we have 1, since we are blocking here the current, and then all the current goes here in the output. 0 and 1. First condition, 0 in input, 1 in output. If we turn on the transistor, what we have? We create a sort of wire here, and so all the current goes through to the emitter. And so here we have 1 since we power on the transistor. So we create a sort of wire here. And then all the current, all the voltage that we have flows to the emitters. And then in output, we have 0. Second condition, 1 in input and 0 in output. That's all. Okay, this is the only one example that we see together, just to understand that it's possible to use transistors to implement the logical behavior of our gates. So it's possible to create computers. It's possible to build an ALU. It's possible to build a central processing unit. Okay, we use the Boolean algebra to create complex gates, and then we can translate this symbol that maybe we use in our ALU, thanks to the use of transistor in our implemented in our PCB, printed circuit boards. Okay. Here you can see just another representation of the AND and the OR. And okay, here you have the symbol, digital logical behavior, and then you can see here that the AND port is AND gate, sorry, is created using 2 different transistors, and in the same way the OR is created using 2 different transistors. Okay. As I mentioned, we don't use AND and OR in model computers. We use only NOR and NAND. Okay, since in this way we save space. You can memorize only the logical behavior of AND and OR. Remember that for NOR and NAND, you have to invert all the bit in output, since you are applying a NOT gate on the OR. So here, for example, we have 0, and here 1, 1, 1, 1, and here we have 0, 0, 0. The same thing for the AND gate, 0, 0, 0, 1, and then here we have 1, 1, 1, 0. So you can memorize only the configuration of the AND and OR gates, and then you can retrieve the configuration of the NOR and NAND gates using the inversion of the bit. And this is the reason of why we use the NOR gates. For the NOR gates implementation, we use only 1 transistor. Okay, so we can save 1 transistor every time we need the NOR gates. In modern computers, we have billions of NOR gates, so you can easily imagine that we can save space reducing for 1 billion of different transistors the space occupied by the NOR gates. Okay. Do you have questions? Everything was clear? Are you sure? So. Yeah.
Why NAND and NOR, these kind of gates save more space?
Compare the version. Okay, for the NAND is more simpler to build, but okay, simpler to build, but we use the same number of transistors. Okay. For the case of NOR, we have only 1 transistor. So you can see here the image of the NOR, 1 transistor, and here the image of OR, 2 transistors. So we reduce the use of transistor. Okay. Okay, so if there are no other questions, we have finished for today. So we can go home early. Last thing is that I have uploaded on Virtuale the program called Logisim. Unfortunately, I found only the Windows version. So if you have Windows operating system, you can download the Logisim for Virtuale. Otherwise, you can try to find a equivalent version. And Logisim is an educational tool to design and also simulate the behavior of the digital logic circuits, in particular also the digital gates. So you can simulate the behavior of the digital gates. As you can see here, you can have a very simple interface. And I suggest you to download the Logisim, since next lesson you can recreate the content of the slide using Logisim. And also now you can find, for example, that here, I don't know if you are able to see it, but you can find the NOT, AND, and OR gate. So you can play with these 3 different gates to see the logical behavior. That is the same of the behavior that I show you. So okay, also here, if you put 0 on the NOT gate, you have 1, 1, 0, and so, okay? And next time we are going to see together also maybe Logisims if we have enough time, okay? It's only a support for you, okay, to visualize the behavior of the logic circuits and so on. Okay, for today we are finished.
How you doing?